In the next few sections here, we're looking at different types of reactions. And we're going to start off looking by precipitation reactions in particular here in 4.2. So the question becomes, what is a precipitate? We talked about this last year. Okay, precipitates are the insoluble products formed by a reaction in a solution. So it's not necessarily that you're forming just a solid, but you're forming a solid out of two solutions. Okay, that is a precipitate. Okay, insoluble again meaning solid. Okay, or it's not going to be able to dissolve. So we have some solubility guidelines. All right, and these will tell us about how much of a substance is going to dissolve in a solution or in water to make a solution, and whether or not we're going to form a solid product when I mix two solutions. So if you flip your notes over to the top of the next page, you'll see a chart, and we had this chart last year on the back of your periodic table. But you do not get this chart this year, so you do have to actually memorize this chart for the most part. Okay. There are some ways to kind of help remember these things, and I'm going to make a couple little notes here. When you're looking at Na, K, and NH4, those ones are always soluble, so as soon as you see one of those three ions, which is very common, those are soluble, meaning they will never make a solid out of a reaction in a solution. Same way here, NO3, ClO3, and C2H3O2, those are always soluble, and then you run into these lovely exceptions. So if they are soluble, that means they will dissolve right away, okay, except for a few. And if they're insoluble, meaning they will always make a solid, except for a few. So notice about a lot of these exceptions, what we've got here, especially with the water-soluble ones. We have a lot of silver, mercury, and lead. And then you add to that calcium, strontium, and barium. Okay. We go the other direction of the insoluble. Again, we're looking at alkali metals, which is group 1, which is Na, K, and NH4. And all hydroxides are insoluble. And here again, we have that calcium, strontium, and barium that are always soluble. You have some things that repeat here, which is where you get a couple of these little like sayings. All right, so I'm going to write them out. All right, so here we go. We have halogens are soluble unless they get slammed into a precipitate, which is silver, mercury, and lead. Slam, SLM. Okay. Sulfates are always soluble unless they get Basker slammed, which is barium, strontium, and calcium. And the only hydroxides that are soluble are the ones that be soluble. And those are that B that we looked at with the strong bases formed with your alkali and alkaline earth metals. Okay. So those are a couple of just little sayings that people will help to memorize them. And again, ammonium and your alkali metals are always soluble, and then you've got carbonate, phosphates, sulfites, chromates, and sulfides that are always insoluble. Okay, and those are up there in that chart. So let's try and classify some of these as soluble or insoluble. So I've got Na2CO3. The easy part with this one, if you look right here, Na is always soluble. And look at lead sulfate. Okay, the key thing here is lead. All right, lead is one of those exceptions to things where it'll pretty much be insoluble. And what I said earlier is that sulfates are soluble unless they get Basker slammed. So it's not barium, strontium, or calcium, but it's part of the slammed, SLM. And it is the L with lead. So this one is insoluble. If I have cobalt-2 hydroxide, okay, the only hydroxides that are soluble are the ones that be soluble, which means that it's going to be insoluble. Cobalt is not part of that B on the alkaline earth. Barium nitrate. Nitrates are nice because nitrates are always soluble. And then I've got ammonium phosphate. Ammoniums are always soluble. All right, we're going to look at exchange or metathesis reactions, or you can call them double replacement or single replacement reactions. And we're going to look at double replacement here. Sometimes they're called either one of those two names, though. Many precipitation and acid-base reactions have that particular pattern where they switch partners. Remember, if there are double replacements, so two things are swapping. Notice how we have AX and BY, the X and the Y have switched. You're not putting the A and the B together, though, because those will be representing two metals. You've got to have a non-metal and a metal. Okay? So predict the identity of the precipitate that forms with solutions of BaCl2 and K2SO4. Write the balance equation for the reaction. So I've got BaCl2 plus K2SO4, and we're going to double replace here, so two things are going to switch. So my barium is going to go with the opposite, with the sulfate, not with the potassium, because they're both positives or both metals. So I take Ba, I put that with an SO4. Look at my charges. Barium is always a 2+, sulfate's always 2-, so I'm good there. Plus my potassium plus my chlorine. Remember from last year, subscripts do not carry over. Subscripts come from the charge. As soon as you put two new things together, you can't carry a subscript over. K is a plus, Cl is a minus, so those are balanced that way. I need to put a 2 out in front to balance the 2 Ks, the 2 Cls on each side. But it's not a subscript. So now I need to figure out if there is a precipitate here. So KCl, all right, the halogens are soluble unless they get slammed. That's not silver, mercury, or lead. That's potassium, so that one is a solution, or AQ. Barium sulfate. Okay, sulfates are soluble unless they get Basker slammed. Well, this is the Ba in that, so that's going to be a solid. And it says solution, so these two originally were also aqueous. All right, go ahead and try the next two. All right, take a look at the first one here. All right, I've got iron sulfate, lithium hydroxide, and then they flip-flop partners, and you got to balance it. Okay, the solid here is iron hydroxide because the only hydroxides that are soluble are the ones that be soluble, and iron's not part of that B. Okay, and the sulfates are soluble unless they get Basker slammed, and so that's not one of those SLM or BASRCA. Will precipitate form with solutions of barium nitrate and potassium hydroxide? No, because barium hydroxide is one of those hydroxides that are part of the B soluble. K and NO3 are never soluble, so no. We're going to take a closer look at equations. We have a molecular equation, and a complete ionic equation, and a net ionic equation. So we're breaking apart what is actually important in a reaction. We start with a molecular equation. So if I take, for example, lead nitrate, we'll look at lead 2 nitrate. I'm going to add to that potassium iodide, and I'm going to make lead iodide and potassium nitrate. This is a molecular equation. Every molecule is represented. All right. And I'm going to tell you, and the problem with these two are both solutions. Okay, KNO3 is a solution because NO3 and K are never soluble. This is a solid because the only halogens that are insoluble are the slammed, silver, mercury, and lead. This is lead. All right. So in an actual reaction in my beaker, okay, if this is a solution, that means that they are dissolved and they are dissociated. Okay, remember, ionic dissociate because they are strong electrolytes. So that means in an actual beaker, you don't have lead nitrate potassium iodide. I have lead ions as a Pb, okay, it's a 2+, and nitrate ions. So remember, when we break this apart, okay, to a complete ionic, I have the lead, it's a 2+. And how many nitrates do I have? Well, I have 2, so we go plus 2 NO3-. My Ki breaks apart, it's ionic, strong electrolyte, okay. So I have K+ and I-. Well, how many Ks and I's do I have? Well, I had 2 Ki's, which means that when they break apart, I have 2 K's and 2 I's, not a subscript 2. Subscripts indicate that they are bonded together. They are not bonded together because you're breaking these apart. Okay, I'm going to stick together my solid because if it's a solid, they're bonded together. I can see it. It's not dissociated or dissolved. I keep that together. Plus 2K+ and 2 NO3- because again, those are ionic bonds. They break apart. It's a complete ionic because you see every single ion. Okay, so then we have a net ionic equation, which means we're looking at the net or the overall or what we are actually trying to look at, what's important, what's actually doing something in the reaction. Well, the only thing that didn't break apart is this solid. Okay, everything else cancels. So, because I have 2 NO3s on the left, 2 NO3s on the right, I have 2 K+ on the right, 2 K+ on the left. So my net ionic will look something like this, and they are solutions, so they get a little AQ. On your AP test, they don't make you write those. And that is my net ionic equation. So these things that we all cross out here, we call those, remember we talked about this last year again, those are spectator ions because really they are just spectating, they're just watching, they're not actually participating in the reaction. They play no direct role in what's going on in this reaction. I could have had sodium there and it wouldn't have made a difference. So those are spectator ions. All right, go ahead now and try the next two. All right, and the first one, you're in the net ionic between calcium chloride and sodium carbonate, and they are both solutions, so you can have AQs here if you would like. Calcium carbonate is the solid because carbonates are always soluble, or insoluble, sorry, and Na and Cl are always soluble. So you could break everything apart if you would like. You'd have Ca2 plus 2Cl minus plus 2Na plus CO3 2 minus yield CaCO3 plus 2Na plus 2Cl minus. And you would realize that the Na and the Cl on both sides cancel. And you're left with just this. Like I said, you can put the AQ in here. If it tells you to, on your AP exam you will not have to. I will often ask you to, though, to put your actual states of matter there. Silver nitrate and potassium phosphate. And again, I kind of skipped the middle one. As soon as you know what the precipitate is, which I know is this Ag3PO4, because K and NO3 are always soluble, then I know that what's going to go into my reaction is going to be the 3Ag plus and the PO4 3 minus. And again, with your states of matter, unless they ask you to put them there.